This video we're going to talk about how we'll solve the finite difference equations that we talked about in video 4.4 for all the unknown temperatures. So there are several ways of solving systems of n equations with n unknowns. Gauss-Seidel is just an iterative method which can handle systems of equations with very high n, very high numbers of equations and unknowns. So consider a system with three equations, three unknowns, t1, t2, t3. And what you notice is that there are subscripts associated with the coefficients a. And the meaning of these will make sense shortly. Next thing that you'll do is you'll put that in matrix form. Notice how we've organized this. If you took linear algebra, you'll recognize this format, but if you didn't, don't worry. It's pretty easy to see how we got here. And those subscripts now make more sense. The first subscript on those coefficients, and for the t and b values for that matter, refer to the row of the matrix. If there's only one subscript, such as can be seen for t and b, those subscripts only refer to the row, and it follows that there are not multiple columns. The second subscript refers to the column. So take a few minutes to see how we can go back and forth from the set of equations to the matrix form. Now, one very important thing to make sure you do is to arrange your equations such that none of the coefficients on the principal diagonal are 0. Otherwise, this method will not work. So in this case, a11, a22, and a33 must not be equal to 0. In fact, if the absolute value of the coefficient on the main diagonal is greater than the sum of the absolute values of the other coefficients on the row, the matrix is diagonally dominant, and the Gauss-Seidel method is guaranteed to converge on a solution. So the highlighted diagonal is the principal diagonal. So if you would have a diagonally dominant matrix, if the absolute value of a11 is greater than the sum of the absolute value of the other coefficients on that row. Same for the other rows. For most, if not all of the heat transfer problems that we'll work with, we'll be able to arrange our matrix such that it is diagonally dominant. And even if we can't, it doesn't mean that Gauss-Seidel won't work. It just means that we're not guaranteed to converge on a solution. So we have our principal diagonal highlighted in different colors, and we have the corresponding t values for that row in the same color. If you're colorblind, don't stress about this. It's just for additional clarity purposes only. So we're going to rearrange all three equations to algebraically solve for each of these temperatures, and we're going to start with some initial guesses as to what those temperatures are going to be. And then based on what that tells us, we'll improve our guesses so that those we'll improve our guesses for those temperatures and keep doing that until we converge on a solution. So let's take our first equation. I'm going to rearrange our equation and solve for T1. Now remember, the temperatures are the unknowns here. The A and B values are just numbers you know. So in order to solve for T1, I need to make a guess as to what T2 and T3 are. I make an initial guess as to what those values are. Let's just guess at 0 for both of the temperatures. I could certainly make a more educated guess if I knew something about the physical situation, but let's just go with 0 for now. I can plug in my initial guesses and I solve for T1. It's not my final answer, but it's a good guess as to what T1 might be based upon my initial values for T2 and T3. Let's move on to solving for T2. I rearrange to solve for T2, and now I make a new and improved guess as to what T1 and T3 are. T3 hasn't changed since I have no new information about T3, but I have a good guess as to what T1 might be. I can plug things in, and I get a new and improved guess as to what T2 could be. Now let's move on to solving for T3. I rearrange to solve for T3, and now I use my newly calculated guesses for T1 and T2 to calculate what T3 might be. And at this point, I have 3 educated guesses as to what T1, T2, and T3 might be. So let's start the process again, but go back to solving for T1. I can take my governing equation on the first row. I solve for T1. I plug in my newly calculated educated guess for T2 and T3, and I solve for T1. and I'm ready to repeat the process for T2 and then T3, and then I can start with T1 again. And then I keep on going as long as I can. Just kidding. I'll repeat the process until my guesses for T1 and T2 and T3 start not really changing that much with each new educated guess. So maybe during the 15th iteration, I see that T1 is equal to 101.3 degrees Celsius. And on the 16th iteration, T1 is 101.31 degrees Celsius. And on the 17th iteration, it's 101.305 degrees Celsius. And same thing would apply for T2 and T3. So I'll pick a very small number called the Convergence Criterion. We'll pick a Convergence Criterion of 10 to the negative 6. We'll ask ourselves if this statement is true for all t values, T1, T2, and T3. So if the statement is true for all values, you can stop. A solution has been obtained, and those last educated guesses for T1, T2, T3 are your final answers. So you might be thinking that this looks like a lot of work. 15 or 16 iterations and maybe even more will be required to reach convergence. So what am I expecting from you? Well, on a test, I could ask you to show me the first several iterations. I could say with an initial guess of T2 and T3 being a certain value, what's T1? What are the next two educated guesses for T2 and T3? In other words, I tell you to show one full iteration for T1, T2, T3. For homework, you should be able to actually use this numerical technique. I'd suggest actually writing a little program in MATLAB that uses this method. You don't have to use MATLAB. I do it in Excel, which shows me each value for the temperature for each iteration until my convergence criterion is met. Example 4.3 in your textbook might be one to use to make sure that your code works. You might remember another numerical technique for solving equations, and maybe you're familiar with the Excel equation solver or some other solver. Can you use that for homework? Sure, you can do that, no problem. But you should be familiar with how this method works. So, well, I hope that was helpful. Thank you for watching, and let me know if you have any questions.